Okay, we're back. This is for check-in number 2 for AP Physics C. Electric potential is the topic for this one. Okay. Go ahead and take a look at this picture. We'll try to explain it and then see if we can figure out the answers. You have two charged spheres. One has a charge Q1. The other has a charge Q2. They're both positively charged and separated by a distance r. What is the net electric field at a point halfway between the two? The charges are the same. So what is the electric field halfway between? If you take a look at it, this is a vector problem. The electric field is defined to be away from the positive and toward a negative. So at the halfway point, the one on the left has an electric field that is in that direction, whereas the positive on this side, Q2, has an electric field in the opposite direction. Looking at the picture, if the electric field for a point charge or a charged object is going to be equal to KQ over R squared, and the distance between those both is like R over 2, I think what's going to be true is that in a vector sense, they both have the same magnitudes. I think the overall electric field between the two halfway has to be 0, because they'll both have KQ over R over 2 squared, and they should cancel each other out because there's the same magnitude of charge on each. Hope that makes sense. Same situation, but now the question is asked if you have these two charged spheres and they have the same amount of charge on each. So again, it probably should have been written down that Q1 equals Q2. And it would be safe to say that you could just call it Q if you wanted to. What is the electric potential at a point halfway between? Now it's a little different here because the electric potential is a scalar quantity, which for a point charge or a charged object would be equal to KQ over the distance, R. So if you're trying to calculate what the total potential would be, then it would be the potential for the first plus the potential for the second charged object. So it would probably look like KQ over R over 2 for the first one, plus KQ R over 2 for the second. Again, I was hoping that we'd realize that they were still positively charged objects. Then the potential away from that is a scalar quantity. They're just going to add up together. And so the 2's will pop to the numerator, and the total charge would be 2KQ over R plus 2KQ over R. Seems to me that's going to give you 4KQ over R as the answer to that problem. Hope you see the difference between the scalar electric potential and the vector electric field. Okay. Next question. You now have two charged objects that are different in size. This one's an R. This one has a size R1, the one on the left, the one on the right, R2. That's smaller. Let's take a look at what the charge is. The charge on the first object is 8 times some number Q, and the charge on the second one is -2 times that same amount Q. -2Q and 8Q. And the distances are that R1 is twice the size of R2. Well, the first question asked, what is the distribution of charge on each sphere? So take a moment, see if you can figure out what your thoughts are for that. And then if we think about it, how is the charge distributed? The distribution of charge should be equal on the surface. So it's a conducting object, so it's got to be on the surface. It's equally charged throughout. Now, we're not saying that there's the same amount of charge on each of the two spheres, but throughout each sphere, it's equally spread and only located on the surface. Okay. Second question says, if the two spheres are connected by a wire, so now you have a wire connecting the two up on the top, by which way does the charge flow, if at all? Well, since there is a charge difference between the two, certainly will be a charge flow. And the question is, which way does it flow? Does it flow one way? Well, we normally think of electrons flowing in a wire. Electrons would flow from negative to positive, or from low potential to high potential. If you wanted to talk about, or you had a question on a multiple choice that said something about the current flow, remember the positive current flow is the opposite. That will flow from positive to negative, and it'll go from high potential to low potential. So be careful what question you're asking, but if you're talking about negative electron flow, it'll go from low potential to high potential. So it goes from low to high, and that would be from negative to positive would be the flow of charge. I hope that makes sense. Okay. Same kind of situation, but the next question is, you have these two charged spheres, and again, R1 is equal to 2R2, and maybe we'll just go back and write again. You've got Q1 is 8Q, and Q2 is negative 2Q. And the question is, how long will the charge continue to flow? At what point will it stop? Well, the answer to that is that it's going to continue to flow until the potential on each is equal to one another. So until the electric potential equals, that's when the charge will stop to flow. It's not when they equal out charge, because these two spheres are different sizes. Therefore, it's not what you would think of if you had two charged spheres that were the same size. They would probably go until they equal or neutralize each other's net positive and net negative charge. But in this case, it will be when the electric potentials are the same. And then the last question we have is, how much charge will be on each sphere when you get to that point where they stop to flow? Okay, so again, we're going to take a look at this, and we might just go ahead and write on another sheet of paper. So we're expecting when the potential on each sphere is the same. So that would be KQ1 over R1 is equal to KQ2 over R2. And the question is then, when we're looking at it, how are we going to solve for that? Because we can write a couple things down. We know that Q1 equals 8 times Q, and Q2 originally was negative 2Q. And then R1 is twice the size of R2. So those were our initial conditions that we had. So we're going to try to plug in some of that. Let's take a look. We're saying that those two are going to balance. Well, let's plug in that R1 is twice R2. And if that's the case, then we do have some cancellation that occurs. The K's cancel, the R2's cancel, and that ends up giving you that Q1 has to have twice the charge of Q2. May make more sense because of the fact that you have more space on that sphere for that charge to be located, to evenly spread out. There's got more space, therefore you're going to probably have more charge, and so that net result that we get is good. So it makes sense. The question is, well, how's it going to split? If you have 8Q and negative 2Q, the total amount of charge is going to be equal to whatever's on both of the two, but they're going to split 6Q as a total. but Q1 has to have twice. So basically what you do is, I think you'd split it up into thirds and say that Q1 is going to get 2/3 of the charge, and Q2, or the sphere 1, is going to get 2/3, and then it leaves 1/3 for the other. See if you would agree that by the time you got done with that, if this is 1, you're probably going to have 4Q on that one and 2Q on the other one. And when you add them together, sure enough, that gives you 6Q, which is the end result. I hope that one makes sense. That's it for check-in number 2. Hope you have a good day. Stay healthy. We'll see you next time. Thanks.